Okay, so what in the world is a PDF, right? I mentioned in the last class that a PDF is a probability density function. But what in the world is that? I'm going to talk a little bit about that today and get into some of the stuff that I was mentioning in class. So let's say, for example, we had a graph. And let's say this graph is our PDF, which we're using the notation lowercase p for. So p of x is our notation for the PDF. So this is our x-axis, our output axis, or our p of x axis. And let's say that we were saying how old are people at Holy Cross, right? So if we say 16, right, there's probably like nobody that's 16 at Holy Cross, right? If we say 17, maybe there's a few people that are 17. If we say 18, right now we're talking. Now there's probably a lot more 18-year-olds, a lot more 19-year-olds, a lot more 20-year-olds, right? 21 starts to go down, and 22 there's probably hardly any. And let's keep going, right? And then 23, really few, and 24, almost none, right? And 25, let's say there's basically none. So what you saw was that the height of the bar, right, kind of told us the height of each bar tells us the quantity of Holy Cross students in that age category. And then these here are ages in years, right? So this is basically the concept behind a probability density function, where it's telling you, right, like in general, we'll consider these different, what they like to call events in probability, right? Like we said, landing on heads if you're tossing a coin is an event. And the only other event when you're tossing a coin is landing on tails. So if it was for tossing a coin, it would only be heads and tails, right? And we said, right, half the time you'll get heads, half the time you'll get tails. So that would look like that. And then the y-axis tells us the frequency of those events happening. And that is the basic concept of a probability function, a probability density function, the frequency of those events happening. I cannot think and write at the same time. Okay, so what we do, right, is we can draw a function p of x on there. And so since the y-axis, right, is telling us how many times an event happened, an event cannot happen negative times. That doesn't make sense. So these graphs never go below the x-axis. They always live above the x-axis. And that was the first condition that we see on the worksheet that says p of x is always greater than or equal to 0 for all x. So no matter where you are, right, on the x-axis, it's always going to lie above the x-axis. Right, so what does this mean, right? So we saw that this means, right, remember, the p of x is our notation for the PDF, the probability density function. So the PDF is always positive. Right, so what does that mean? Like I just explained. Therefore, right, since the function is always positive, right? Or what does that mean, right? That means that it's above the x-axis. Remember, all areas above the x-axis are positive, so its integral is always positive as well, right? So we get that the integral from a to b, right, any a and b of p of x dx is always greater than or equal to 0. And then it's so important to combine this with the third property on the worksheet, right? Because note that since the probability itself, right, the probability that a lies between x and b is equal to that integral of p of x, right, we also get that the probability is always greater than 0, which is how we defined probabilities to begin with. And when I introduced this topic in the last class, right, probabilities are always positive, because what would it mean for there to be a negative chance of something occurring? That doesn't make any sense, right? So this makes sense since probabilities are between 0 and 1, right? And remember that this here is our notation for the probability of x being between a and b. Okay, so then let's move on to discuss the second property of PDFs on the worksheet, which says that the integral from negative infinity to infinity of p of x dx is equals to 1. So if we look at the graph, what does this mean? That means that the area, right, under this graph, if we consider the entire x-axis, any area under the graph of p of x sums up to 1, which makes sense because remember that we multiply the probability by 100. So when we say that it's equal to 1, the probability is equal to 1, that means the probability is 100%. And remember that if this is going to exhaust all of our options for events, so if we consider the whole number line, then we're saying, oh, any possibility, if we consider all the possibilities happening all together, that's 100% of the possibilities of events occurring, right? So this means that the total area under the graph of p of x is equal to 1, right? And recall that the integral, right, is the area under the graph. So that's how we connect these two dots. Right, so again, what this is saying is that the probability that an x value is between negative infinity and infinity is equals to 1, right? Because remember, this is equal to the integral. The probability is equal to the integral of p of x. And so, right, the value of x has to be somewhere on the number line. Okay. Let me write that down actually. Right, so the value of x has to be somewhere in negative infinity to infinity, right? Somewhere on the number line. So the probability of that occurring, right? The probability that x is between negative infinity and infinity has to be 100%, right? Which is equals to 1. When we're talking about what comes out of the probability, the integral of the probability density function. Okay, and then the last point, the third point, right, is what allowed us to really connect these two dots in number 1 and number 2 here. So that's why I wanted to introduce it in class, right? So what we're saying is that the probability that x lies between a and b, right, or like the ages are between 17 and 18, is equals to the integral of that probability density function, right? So if I wanted to look at this example again, and I wanted to see what's the probability that people are between 18 and 19, well, that's whatever this integral is equal to in between here. Okay. So this tells us basically that we can compute the probability that x lies between a and b by integrating the probability density function p of x from a to b. So basically our relationship is that the probability that x lies between a and b is synonymous with the area under the PDF between a and b, which is synonymous to the integral of p of x. Right, so the important things to take away is that probabilities are always between 0 and 1, which also translates to the fact that the area under the curve of a PDF is also between 0 and 1. So I want to just give a few hints for like exercise 1 and 2 just to get you guys started. So exercise 1, right, the first hint is going to be that you need to make sure that the p of x given satisfies all of the properties discussed, right? Properties 1, 2, 3 in the definition of PDF. For your choice of capital C. And then the second hint is to notice that p of x is 0 for all x values between negative infinity and 0, right? It says if x is less than 0, then p of x is equal to 0. So this means that negative infinity to 0 of p of x dx is 0. right? Because if the and then I'm just going to say to also keep in mind that you need to ensure that the integral from a negative infinity to infinity of p of x dx is equals to 1. So remember the properties, right? And look at these, pay close attention to these bounds and how you could split up the bounds. And then for exercise 2, again, you need to show that p of x is, right, meets all of the PDF properties, right? The 3 properties we discussed. And since they tell you that k is greater than 0, then you know, right, that f of x, since it's equals to k e negative kx, right, you know that this is positive, and then you know this is positive, right? And the exponent being negative is not going to make the whole entire number be negative. So you know that f of x is also positive. And also use the hint from the last exercise. All right. Hopefully that's enough to get you guys going on the worksheet. Let me know if you have any questions.